Hi, I'm Cora Todd, Project Manager for Katerra Construction, and this is the South Landing Catalyst Building. And I'm excited to take you for a tour. Let's go take a look. In the Catalyst Building at South Landing, it's 160,000 square feet of Type 4 heavy timber construction. We use glulam beams out of Canada, and we use 3 different sizes of CLT in this structure. The 7-ply shear walls are by StructureLam. The 3-ply exterior walls are also by StructureLam, and the 5-ply floor panels, both in flat panel and built-up double T panels, are from right here in the Spokane Valley out of our Katerra CLT factory. It aims to be one of the largest zero energy and zero carbon buildings in North America and will pursue zero energy certification by the International Living Future Institute. The 5-story office building is a result of a cross-industry team of partners, including utility provider Avista, design-build engineering firm McKinstry, and Katerra. Working with Katerra design partner Michael Green Architecture as the design architect, Katerra is the architect of record and general contractor for the building. The building makes extensive use of CLT in design and structural elements, including floors, shear walls, and building envelope, which enables near passive house levels of thermal performance. So let's start by looking at the 7-ply panels from StructureLam. 7-ply shear wall elements erected in 2 lifts using a spliced epoxied rod system allowed for ease of erection and constructability. We were able to gain quite a bit of schedule using this system, even having to do a half-lap joint in the middle to span the lengths that we needed. And you can see here, this is where these 2 panels splice together and the screws tie them to each other. Katerra needed to use 7 and 3-ply panels from StructureLam because at the start of construction and when we needed to start producing materials, Katerra was only certified to produce 5-ply panels. We have since then received our certification to produce 3-ply panels and are currently in process for getting certification for both 7 and 9-ply panels. 10 by 30 3-ply exterior wall panels from StructureLam are built up of 3-ply CLT, rigid insulation sandwiched in metal panel, plus a rain screen system that has terracotta panels on the very outside. This was important, according to our acoustics engineer, in order to minimize the sound transmission of the active railway to the north of this site. The 3-ply panels came to us with window cutouts already present. We then installed punched window openings, which are triple pane units from Euroline windows in Canada, and the exterior envelope has an R40 average because of the minimal thermal bridging as a result of the CLT. The use of CLT in exterior walls of Type 4 heavy timber buildings is allowed. Katerra worked diligently with our code consultant and the City of Spokane to ensure all fire life safety measures were addressed with regard to flame spread. The floor-lined fire stop assembly is typical as found in aluminum curtain wall to concrete deck building. What we can still see, because TI renovations have not begun on this floor, is the gravity connection steel plate connecting the CLT 3-ply to the perimeter glulam beam beneath this gypcrete. The primary tenant for the building is Eastern Washington University. They occupy approximately 60% of the building. EWU is relocating some of their technical programs to this building, including computer science and electrical engineering, ideal programs to be located in this type of structure. The grid was set up on a 30 by 30 spacing, which while not completely efficient for CLT, we were able to manage well by using ribbed panels, essentially a double T made from wood fiber instead of concrete. To our knowledge, this is the first application of this technology in the US. The Catalyst building utilizes the very first product off our factory floor. Not a single panel was sent back. We are 100% on quality for our first project. Every piece of wood that you see in here is an SPF or a spruce pine fir mixture. We upsized the glulam beam in the center bays to allow for flat panels instead of the built-up double Ts. Upsizing the center beam allowed for running of mechanical systems through these center bays and then out into the outer bays via the castellated beams that you see here. Low air leakage equates to very high performance. It's the metric that tells you how the building will perform and whether it reaches the very minimal energy allowance of a passive house building. Passive house needs to have uncontrolled leakage through gaps less than 0.6 of the total house volume per hour during a pressure test at 50 Pascal, both pressurized and depressurized. The Catalyst building measured an air leakage rate of 0.035 CFM per square foot, which is significantly below the code requirement. The results demonstrate the great workmanship and management by the Katerra construction team and rigorous detailing by the design team. Air tightness is difficult to achieve in a building of this size. Air tightness tests were done by RDH, one of the leading envelope design firms in North America. They have done over 100 similar tests, and the Catalyst building performed better than any building they have ever tested. Integrated wood slat system from Okalux was important also to achieve the passive house rating. You can see demonstrated that while I have sun coming through my punched window openings, we don't have sun coming through this very large curtain wall space. On top of our CLT panels, the floors have a 3/4 inch Acoustomat and 2 1/4 of Gypcrete on top of that. This was done in order to minimize vibration from pedestrians and people walking through the structure. Panel to panel spacing, behind this piece of trim, we still have about a 2.5 inch gap, which allows for interstory movement of up to 3/4 of an inch per panel. So if in case of an earthquake, these panels would shift independently and not conflict with each other. One of the structural elements in this building is called a BRB, a buckling restrained brace. There are 22 of these at our shear course. These are concrete-filled steel tubes that have steel plates running through and basically act as a stabilizing tool that if this building were to start rocking in an earthquake, they take the forces from the diaphragm above and drive them into the very large concrete pads that we have underneath this stair core. And that happens at all 3 of our stair cores and at the knife walls in between throughout the structure. We added an extra beam at the center bay to eliminate rib panels within the center zones to allow for main distribution around the core above the corridor, then feeding branch ductwork through cutouts in the main glulam girders. The CLT within the core is an efficient span of 15 feet. The omitted beams allows utilities like ductwork to be installed tighter to the underside of the CLT. An environmentally conscious choice in this structure included capturing waste that could have gone through the chipper and utilizing it for other parts and pieces in our building. This included getting the window cutouts that came from our 3-ply panels and utilizing them for my stair treads and risers and landings in these stair cores. The finished surface in this area is going to be a rubber tread and riser, but then the underside of the CLT is all going to stay exposed. This is an example of part of the tenant build-out that Eastern Washington University has done in the Catalyst building. This is a Bdc Classroom, and it showcases the cloud system by Overcast Innovations and installed by McKinstry. The goal was to maintain open space while distributing electrical, mechanical, and fire alarm systems throughout the space. Commercial buildings are not required by code to provide for perimeter power. Katerra Design worked closely with McKinstry to develop strategies for routing conduit across the ceiling, through perimeter beams, and down the exterior wall in discrete locations when necessitated by future tenant fit-outs. Most office systems and layouts are serviced by floor boxes or through adjacent framed walls, which omits the need for such perimeter power and data. In this main lobby between East Tower and West Tower, Katerra and Michael Green Architecture really wanted to emphasize vertical wood elements as well as CLT panels that extend past the perimeter of the building via our cantilevered awnings. While the majority of this building is made out of wood, in this 2-story lobby, we did have to use steel elements. That steel, because it's exposed, needed to also have an intumescent coating applied before we put the finished paint on it. Now, the floor panels of level 3 create this lobby space, and Katerra thin 3-ply panels are then used as a veneer to expand between rib beams. When we put 3-ply panels from beam to beam, we created a concealed space. And because of that, Katerra had to use a fire-resistant coating because that area is not sprinkled. Katerra commissioned the Carbon Leadership Forum and Center for International Trade and Forest Products at the University of Washington to analyze the environmental impacts of our CLT as well as the Catalyst building in Spokane. These two organizations are the preeminent leaders in their respective fields. CLF recently released an embodied carbon calculator for the construction industry, and Sintrafor is well known for its research to support sustainable forestry and forest products trade. Our goal in pursuing this analysis was twofold: to better identify opportunities to reduce environmental impacts in our supply chain and improve CLT production efficiencies, and to eliminate the life cycle environmental impacts of mass timber at the whole building scale, identifying opportunities to optimize the environmental performance of mid-rise mass timber structures. The Carbon Leadership Forum found that mass timber nearly offsets all upfront embodied carbon in the Catalyst building. The life cycle assessment of the Catalyst building structure and envelope estimated the upfront embodied carbon of the building to be only 207 kilograms of carbon emission per square meter. Considering the Catalyst building stores approximately 204 kilograms of carbon per square meter of biogenic carbon, the CLT and glue lamp elements offset its upfront embodied carbon. While the study did not make direct comparison of the Catalyst building to similarly sized buildings constructed out of steel or concrete, its upfront embodied carbon impact is significantly lower than that of other North American commercial office buildings in the embodied carbon benchmark study. So a thing that was important when applying quite so much hard surface in this main, very tall lobby area was that we had to use quite a lot of sound insulation board behind all of the horizontal and vertical panels to make sure that while this was an open space, it's not a loud space. So now we're out on the north patio in order to show you first how our Katerra CLT panels look in the cantilevered awning, but also to show the Alaskan yellow cedar siding showcased on the north and east elevations. So here we are on the level 2, soon to be occupied deck for the Catalyst building in order to show you the Terracotta rain screen system by Schilden that we ordered out of Germany. This system uses a vertical clip and rail system in order to take these approximately 3 feet by 1 foot panels and hold them in place.